நீங்க எல்லாருக்கும் குரூப்ல ஜாயின் பண்ண சொல்லி போட்டுலாம் வாட்ஸ்அப்.
Good sir.
Good afternoon, Professor.
Good afternoon, sir. Good afternoon, sir.
Right on time, sir. Audience, we have an eminent researcher from Vellore Institute of Technology. I am greatly honored to have his introduction read by myself. Dr. A. Satish is currently working as professor in the School of Mechanical Engineering in Vellore Institute of Technology, Vellore. He has completed his PhD in metal hydride-based hydrogen energy from IIT Guwahati, India. He has completed in the year of 2011. Dr. Satish has a rich research background with more than 50 peer-reviewed journal publications and more than 30 conference publications, which comes in the form of proceedings. He has presented his papers in various forums, national and international. Under his guidance, 7 PhD scholars have completed and 5 research projects from the funding agencies in India, like GETSD and the MNRE, have granted him a huge grant to the tune of about 1 crore. From national and international funding. Apart from the national, he has also fetched Erasmus, CBHE and the British Council and global partnerships have been made by him. For the industry academia collaborative grant, also he has fetched amount, and for the grant he has also fetched the top-up grant also. To tell a few completed projects, DST funded project is one among them, which is in this zone of hydrogen energy. The compression and working of green energy technologies is his favorite working plate. He is one of the person who completes such projects under ANRF PAR scheme, and Dr. Satish is holding 2 Indian patents and actively engaged in the consultancy projects in motor cooling systems and flow analysis of engine exhaust manifolds. So with this short profile, I will let the podium to be handed over to Dr. Satish to take the session on hydrogen storage technologies, the role of metal hydrates in modern application. Thank you, sir. Welcome, sir.
Thank you, sir. Thank you for giving a brief. Shall I share the screen, sir?
I'll just take a snap of yourself with the screen on.
Yes, sir. Sure.
Sir, I'm stopping my screen. Thank you.
Sir, can you be able to see my screen?
Clear, sir. The screen is clear. You can maximize, sir. Thank you, sir.
Yeah, thank you, sir. Thank you very much for giving the nice introduction. So I'm Dr. Satish, Professor, School of Mechanical Engineering, Vellore Institute of Technology, Vellore. So next 1 hour or 1.5 hour, I'm going to give you a brief about the latest trend, hydrogen storage technologies, the role of metal hydrides in modern applications. Of course, we all are focusing on energy demand, and at the same time, we are concerning about the environmental aspects. So based on this scenario, hydrogen is identified as one of the best and alternate energy source. So before going to the presentation, where we are and how we have used the energy in various modes. If you see here, primary energy consumption which was started from the beginning. Based on this, the demand has steadily increased. If you see here, fossil fuel and non-fossil fuels steadily from 1965 to maybe till late, and the future prediction. So steadily increasing still, which we are consuming the oil, gas, and the coal also steadily, which is increasing. But however, the share of renewable energy, if you see here, which is drastically increasing from 2000 and 2000 onwards. So if you see here, the utilization of solid fuel and gaseous fuel, maybe in the beginning of 1960s and 70s, which was compensated one to other due to the need of our energy. But by that time, environmental aspects was not focused in depth. The reason was the power consumption per capita was very less. But if you see, maybe now nearly 3 times the power consumption per capita is increased. Roughly 3 kilowatt hour is consuming per day per person today. But if you talk about maybe 20 years before or 25 years before, we never used such energy or in terms of electricity, because of increase in transportation and also industrial needs. The energy demand is progressively increasing. So you can see here, the fossil fuels are gradually depleting, of course not that much steadily. However, at the same time, due to the increase in energy demand, we are focusing on other modes of the fuel, which may be related to the renewable, which is not depleting on the earth. But if you talk about coal, oil, and gas, over the consumption, those are depleting over the duration. So you can see here, electricity installed capacity in India for the different modes. Probably in the last 10 years, if you see here, coal-based and renewable-based was dominating. Maybe 327 gigawatt of capacity was consumed in 2016-17, but now maybe 23-24, it is 44-42 gigawatt of electricity we are consuming, which shows that nearly 1.5 times steadily it is increased. But however, if you see here, maybe based on the coal-based, 192 gigawatt was installed, but now the increase in coal-based electricity consumption is very limited as compared to the renewable energy based. The renewable energy based, you can see here, maybe 100 gigawatt roughly, to almost double the electricity capacity is produced from the renewable based. So we can see here, as of now, maybe 25-26 installed capacity is almost 510 gigawatt, which is almost above 50% of the capacity we are producing the electricity from the renewable energy. So it is around 262 gigawatt. Why we want to focus renewable energy? So we all know that we have concerning about the globe earth, how that will sustain due to the pollution. So if you see here, maybe in one aspect, if you see oil, natural gas or coal, those resources will be depleted in the maybe another few decades, or maybe in another 100 years, while the hydro and nuclear energy have environmental and safety concerns are there. If you store the nuclear based fuels, we need a highly sophisticated storage method, maybe under the water, 500 meter or 1 kilometer depth. We need to store the uranium based fuel. So by seeing all those aspects, the energy production from the fossil fuel, if you see, basically burning the fossil fuel, of course we are getting the energy, but it causes the pollution. Because of this reason, the greenhouse gases are producing from the burning fossil fuels, which are CO2, methane, NOx, and SOx, so and so gases. So what happens, this greenhouse emission or greenhouse effects, which rises the earth temperature progressively. You can see here the global earth temperature is increased during 20th century by 0.76 degrees Celsius. The rate of increase of temperature is 0.2 degree per decade. So if it progresses in future, maybe in another 40 to 50 years, the earth temperature may be still very high. It may lead to 1.5 degree to 2 degrees Celsius. So if it goes, what happens? Close to the northern pole or southern pole, the icebergs will melt. Due to that, global sea level may rise, and because of that, maybe the monsoon may not be predicted as per the regular time duration, and the droughts may rise. Global sea level will rise by around 0.18 to maximum of 0.59 meter in the another 50 years or 100 years, and we cannot predict the cyclone and the typhoons due to the rise in global temperature. So this may be the main cause of global warming. So because of this, we need to save the environment by reducing the global temperature. So for this reason, United Nations has come up with 17 sustainable development goals. They provide a clear blueprint right from the first goal to 17th goal. What are the things we must focus right from 1 to 5? If you see the basic need for human being living in the earth. So no poverty, definitely zero hungry, good health and wealth being, good education. Of course, good education will lead to the good society, gender equality. These are all very, very basic things that everyone should get across the globe, and which provides the clean water, affordable clean energy, decent work, and industry innovation and infrastructure up to 10. These are the maybe the intermediate or medium level. Whoever will achieve goal 1 to 5, they will focus in that. So which leads to the society from 11 to 17. So if you see all these things, probably not only the human being, and also the species living under the water, and also land, birds, peace, justice, everything is covered in the 17 sustainable goals. So which was implemented in 2016, and the target duration of 15 years was fixed by the United Nations. So if we talk about the hydrogen energy, particularly to overcome the pollution or environmental aspects, these 4 sustainable development goals will come under the hydrogen energy. So sustainable development goal that will give you the good education, which leads to hydrogen utilization in various aspects, industrial side, transportation side. So because of the utilization of the hydrogen energy, we will achieve the clean and green environment, and industrialization also will develop based on the need, and also sustainable cities and communities can be developed or achieved in future. So why hydrogen we are focusing particularly for alternative fuels or industrial needs? Because we know that energy is increasing progressively. So in last 20 years itself, I said nearly 3 times per capita energy consumption was increased. So if we talk about 2050, then definitely it would be still again double the time, means 6 kilowatt hour or 7 kilowatt hour minimum may be required. So how to meet out this energy demand? In the other side, if you see available of fossil fuel, we don't know how that will sustain due to the depletion and scarcity. So by seeing this scenario, hydrogen is one of the best alternative. Why we are identifying this hydrogen means which is available plenty in the universe, particularly in Earth, because this hydrogen can be extracted from water and also methane, which is not available directly, but with some processes we can able to get the hydrogen in the purified form. If you see the hydrogen which is having a high gravimetric energy, nearly 3 times higher than the petroleum products, and also which is environmental friendly, and it forms water. If you burn the hydrogen, byproduct will be the water vapor, and also high energy conversion efficiency if you utilize it for fuel cell applications, nearly 90%. So these are the reasons that hydrogen can be identified, but major challenges are storage and how it can be used for the transportation, that is mobile applications. So renewable energy, particularly if you talk about the hydrogen, there are various modes. The hydrogen can be extracted from coal, natural gas, biomass, and from the renewable sectors, solar PV, hydrogen. From those approaches, we have some processing technique. Maybe one of the processing technique is electrolyzer. Similarly, steam reforming and biogas. From the biomass we can extract the hydrogen. So from the top side you can see the supply, what are the various modes that hydrogen can be extracted, and the bottom side demand, how it can be meted out. So you can see here transport, one sector, buildings, and industrial side. There are various subdivisions are there. Those can be obtained with the help of fuel cell. Electricity can be produced, and that electricity can be met out for various needs. So as I said, hydrogen is good for various approaches, and various merits are there. And one of the another merit is which is having higher calorific value. You can see here calorific value of various fuels, solid and liquid fuels. Compared with those fuels, hydrogen is having 143 kilojoules per kg of hydrogen. If you burn 1 kg of hydrogen, you can get it around 140 kilojoules. So here nearly 3 times higher than the petrol and diesel and other liquid form of the fuel. Hydrogen is foremost best in terms of gravimetric, but at the same time, since it is the lightest gas by volumetric, this is nearly half compared to the petroleum products. So the challenge arises that how this hydrogen can be stored for utilization of a long duration. Based on the hydrogen production, the color codes were recently given to understand or to identify that what method the hydrogen was produced. You can see here blue hydrogen, green hydrogen, brown, gray hydrogen. There are various color codes are given. So you can see here blue hydrogen was produced from the processing of methane, and the carbon dioxide which is released from the production, which is captured and stored for saving the environment. Whereas for the green hydrogen, in the green hydrogen, the complete hydrogen is processed from the renewable energy, and there is no carbon dioxide is emitted. One of the method is electrolyzer. So from the electrolyzer, hydrogen and oxygen will be splitted. That hydrogen is stored for the required application. So here there is no emission of carbon dioxide or any other gases. The brown hydrogen which is produced from the coal, of course the color code itself says that we need special attention for processing the CO2 and other gases. And the gray hydrogen, of course this is also produced from methane, but the CO2 is emitted to the environment. So like that, the various color codes are identified from the production point of view, how those produced hydrogens can be stored or utilized in the their various requirements that will be shown. So here this slide shows that hydrogen, if we use completely what is available in the environment that we are taking for our need, for our various applications, say for example primary energy. Two, we will get the hydrogen and utilize it for various applications. From that, the final byproduct will be water itself. So basically from the environment, what is available, that we are utilizing it for our need, and finally we are releasing it to the environment as it is without disturbing the environment. So this shows that a complete cycle of the raw material to the end use, only water. Okay, so this is a good example for circular economic approach of hydrogen energy. Whereas coal-based or liquefied fuel-based, which may be the raw material we are taking, burning it for energy production or whatever the applications we want, and finally what we are leaving it to the environment, which will be harming the earth. So that is a sign of a linear economy. But whereas for the hydrogen economy, which leads to the circular economy. So this is one of the approach, this hydrogen based energy we are focusing. So probably if you see, we have seen so far hydrogen production and the various color codes. So if you talk about the cost of hydrogen production, maybe for large scale requirement is lower than the hydrogen storage for the following reasons. If you see, in terms of safety and long-term storage requirement, probably cost of hydrogen production may be less than the storage, and high pressure storage, cryogenic liquid hydrogen storage, and the transportation linked to hydrogen storage. For these reasons, the cost of hydrogen storage will be higher than the cost of hydrogen production. So what are the various methods the hydrogen can be stored? If you see, there are basically compressed gas method, then liquefied method, and other forms like a solid state method. So if you see hydrogen, as I said, for large scale requirement or for large industrial requirement, some situations the cost of hydrogen storage will be higher than the cost of hydrogen production. So how this hydrogen can be stored for a large scale requirement? If you see, one of the method is high pressure cylinder. So we have to compress the hydrogen by electrical energy like air compressor to the elevated pressure. So if you see, hydrogen density is almost 80 grams per meter cube. So in 1 meter cube, we can store the hydrogen of around 80 grams at atmospheric pressure and temperature. So you can think, so only 80 grams of hydrogen, we cannot use it for any, even a small application also. So ultimately what we need to do, increase the capacity by increasing the pressure, or in the other way, decreasing the temperature. So if you increase the pressure from 1 atmospheric pressure to maybe 10 atmospheric pressure, so instead of 80 grams multiplied by 10, you will get 800 grams of hydrogen. So like that, if you increase the pressure as per our requirement, then significant quantity of hydrogen can be stored. Say for example, we want to store probably of 10 kg of hydrogen for the transportation application, that leads to say for example 100 kilometer the vehicle will run means, so we have to compress the hydrogen probably around 500 bar to 800 bar. So how to achieve this much pressure is a big challenge one. So there are some methods, mechanical compression approaches are there, but the cost of compression of the hydrogen to the elevated pressure is high. And if we achieve also, there are various other challenges. So compressing the hydrogen to that elevated pressure leads to, there are chances of explosion, and also low volumetric energy density, as I said, lightest gas. you need a high grade energy, basically electrical energy, to compress the hydrogen to the elevated pressure, and also a sophisticated cylinder is required to withstand such a high pressure. So this is one of the conventional method. Though we can store the hydrogen in this much pressure, there are various limitations are there. In the other side, at atmospheric pressure itself, if you reduce the temperature, then at a temperature of minus 253 degrees Celsius, almost 20 Kelvin, you can get the hydrogen in the liquefied form. So, but if you achieve such a high what is that grade, the hydrogen at minus 253 degrees Celsius, there are various constraints are there. One thing is to get such a very low temperature, you need a cascade refrigeration system to get the liquefied form of the hydrogen, and also the storage container requires a sophisticated insulation techniques. That means the thermal conductivity of the material must be very less, so that the temperature inside the vessel can be maintained minus 253 degrees Celsius. And apart from that, there may be the chances of boiling losses. The reason is inside the temperature is minus 253 degree and outside atmospheric temperature. Due to this huge temperature difference, definitely whatever may be the material you are storing, high insulation material, definitely some percentage of hydrogen will escape from the vessel. So on an average, around 3% of the hydrogen generally can escape from the vessel. In such a situation, you think over the month you cannot get maybe not even 50% of the hydrogen what you stored, simply it is escaped from the vessel. So these challenges we have to come out when you go for preferring the liquid hydrogen. So apart from compressed hydrogen and liquid form of hydrogen, there is another option of solid storage of hydrogen, which is nothing but the hydrogen stored in the material or metal lattices. So here you can see metal hydrides, which are chemical compounds formed when hydrogen gas reacts with the metals. So you can see here there are some materials, lanthanum based, under the Kleck's table, lanthanum based alloys, which are called as a rare earth materials. So when those metals are exposed to the hydrogen will come and contact with the material, it reacts chemically, and the hydrogen will start penetrating into the metal lattices. Since the hydrogen atoms are very small and light, that will penetrate into the metal lattices, forms the metal hydride and releases the heat. So during storage, or we can call it as absorption, heat will be liberated. Basically, it is a exothermic reaction. So whenever we want hydrogen, you apply a little quantity of heat, the hydrogen will be released from the metal hydride. So you can utilize that hydrogen. So because of this exothermic and endothermic reaction, with the selection of alloy, you can able to achieve a minimum of minus 25 degree or 30 degrees Celsius to a maximum of 200 degrees Celsius. So dual application this metal hydride is giving. One is to store the hydrogen in a safest method, and at the same time heating and cooling. Because of the selection of that alloy, heating and cooling can also be achieved. So this is one of the best approach and safest method of hydrogen storage as compared to the other conventional method. So the various approaches, how the hydrogen is absorbed, the physics option initially contact with the metal lattices, and the chemist option slowly that penetrates into the void spaces in the metal hydride. So of course, whatever the material has been synthesized, we need to go for the characterization. That means whether the metal hydride is eligible for storing the hydrogen for our requirement. So this characterization study, basically pressure, concentration, temperature characteristics, shows that whether the hydrogen can be, means the material can be used for hydrogen storage application. Initially, you can see here, metal hydride is filled inside the container and slowly supply the hydrogen at the operating pressure and temperature, which leads to increase the pressure inside the vessel. And once it attains the elevated pressure, the hydrogen will start filling inside the metal lattices. You can see here, this is the beginning stage when the hydrogen is start filling inside the metal lattices. So during that state, the pressure inside the vessel will not increase, rather the hydrogen will be storing inside the metal lattices. So this is the effective storage duration where hydrogen is inside the metal hydride. So this is the preferred storage duration. So once it attains almost all the white spaces, metal hydride hydrogen is filled. So at this situation, whatever the hydrogen you are supplying, that will rather increase the pressure inside the container. So drastically that is increasing. So the region, this is called the plateau region. And if you increase the temperature from maybe atmospheric temperature to high temperature, the entire vessel, the storage capacity will decrease. So with increase in temperature, storage capacity, this plateau region is decreased. So our required duration or required thing is the concentration, where this region we are focusing for the hydrogen storage. So from this, one can able to draw by taking this midpoint of this plateau region and find the enthalpy and entropy. Of course, for any metal hydride, during absorption, the horizontal plateau cannot be achieved. So due to the various reasons, so the slope will be occurred, and also during desorption, there will be the difference in loading and unloading, the hysteresis also occurs. So these properties one can able to obtain by doing the characterization, that is PCA measurement of the synthesized alloy. So these experiments will be conducted. Maybe we can also do the mathematical modeling with this above equations which is shown here, in order to find the equilibrium pressure, the enthalpy, entropy, those alloy properties may be available in the web source, or if you want to do the mathematical analysis based on the experiment, which is not possible to conduct by the experiment, you can extend the numerical study. So these equations are useful to do the absorption and the desorption of hydrogen in the metal hydride. So during absorption, as I said, see here. So this is the reactor which was preferred for solving the numerical modeling. So the dimensions of the reactors are shown here. So during absorption, the above the previous slide equations are shown here. So once the hydrogen is supplied through the inner cylinder here, through the inner cylinder, metal hydrides are filled here. Over that, heat transfer fluid is supplied in a mass flow rate of maybe 2 kg per hour or 3 kg per hour. So here, when the hydrogen is supplied, due to the exothermic reaction, the heat is drastically increased inside the metal hydride. So that heat, how effectively we are extracting from the reactor, the hydrogen storage capacity accordingly will increase. Basically, the rate of hydrogen will increase. So increasing the temperature due to the supply pressure of the hydrogen. Higher the supply pressure, accordingly the temperature inside the metal hydride is increased. So the average bed temperature or the temperature inside the metal hydride can be plotted. So the reason why we are analyzing all these things means to understand the rate of hydrogen absorption or hydrogen storage in the reactor. So you can see here for low pressure, it takes more time to reach the elevated storage capacity, whereas for other cases, you can see the rate of hydrogen storage capacity accordingly with respect to pressure, it is increasing. However, the maximum storage capacity is not changed. See, almost around 1.38% of the storage capacity of hydrogen, which is nothing but this much kg of hydrogen per kg of alloy. Similarly, during desorption, so when the hydrogen is released from the reactor, in the beginning, due to the difference in pressure, quantity of hydrogen will be released drastically. Due to that, the heat available from the metal hydride itself takes, and hydrogen will release very fast as compared to the heat supplied. Because of that reason, the temperature inside the metal hydride reactor decreases well below the atmospheric temperature. So you can see here, for example of 30 degree at delivery pressure of 1 bar, the rate of mass of hydrogen release is very fast than the rate of heat. So because of that rate of high mass desorption, the temperature inside the bed itself takes, which leads to decrease in temperature even less than atmospheric temperature, roughly for 0 degrees Celsius within 2 to 3 seconds. So this approach can be effectively used for refrigeration and air conditioning applications. So this is the setup which we developed at VIT Vellore. Basically, this is the reactor where metal hydride is filled. So hydrogen will be supplied through the connections, and we are monitoring the amount of hydrogen supplied through the reference volume. Initially, we have to vacuumize this entire setup in order to avoid the oxidation of the metal hydride. Then the temperature, pressure, all those things we are monitoring through the pressure transducer and thermocouple through the data logger. So this is one of the sample reactor where we can do the characterization study, and this is the study for hydrogen compression and various applications, hydrogen storage applications. This capacity of hydrogen is 500 grams of hydrogen. Half kg of hydrogen is filled inside this reactor. So in order to remove the heat and the supply, this thermostatic bath was used to transfer the heat. So with this hydrogen absorption and desorption, we can construct various thermal devices which are hydrogen purification, heat pump and refrigeration applications, hydrogen compression, thermal energy storage, and so on. So hydrogen purification, if you talk about one of the prime and important, so whatever the hydrogen is produced from various methods, we cannot expect that all the produced hydrogen is of high good quality. So maybe grade 1 or grade 2, which is of 98 or 99% hydrogen. Along with that hydrogen, there are some carbon dioxide or carbon monoxide may be present in that. So through this metal hydride absorption and desorption approach, we can achieve a purified form of hydrogen, which is the grade 3, 99.999%. So what basically this purification do? The impure hydrogen will be supplied to the metal hydride. So once it is absorbed by the metal hydride, then after complete absorption, you release the hydrogen by supplying a waste heat or solar heat or whatever the heat is available. The moment the hydrogen will start dissolve, it allows only the hydrogen, the remaining gases, whatever impure gases that retains within the metal hydride itself. So after few cycles, this impure hydrogen, impure form of the gases will be purged from the metal hydride. So simply by absorbing and dissolving, we can achieve a purified form of hydrogen in this metal hydride approach. So this is one of the method where hydrogen purification is done. So, so this purified hydrogen gas is a crucial requirement for fuel cell based transportation applications and ammonia production, refining processes, and various other industrial needs. So, as I said, various methods of hydrogen production. If you supply to the metal hydride, basically the absorption will take place. Once absorption is over, then whenever you need, you can release the hydrogen by desorption approach. That can be utilized for our vehicle application or various any other applications. This is one of the method, and second application may be the metal hydride based hydrogen purification integrated with the compression. So compression, the hydrogen compression, unlike mechanical compression, here thermal compressions. So basically hydrogen is absorbed and close all the valves or whatever the connections are there. You supply the heat transfer fluid from probably atmospheric temperature to elevated temperature 80 degrees Celsius or 100 degrees Celsius. The available temperature range at the particular location leads to increase in pressure. So temperature, increasing the temperature is directly proportional to the pressure. So the pressure is also increased inside the reactor. Then you dissolve the hydrogen, such a high pressure hydrogen will be released. So this is another best method of hydrogen compression device, unlike mechanical compression. So in the mechanical compression, hydrogen need to be supplied to the piston cylinder arrangement, where you need high grade energy to compress the hydrogen. When you increase the or when you compress, indirectly the temperature inside the piston cylinder arrangement also will increase. So you have to reduce the temperature by keeping the intercooler arrangement and other things. So whereas here, as per our requirement, the temperature will be increased and the pressure also directly is increased to as per our requirement. So here, this is one of the line diagram that is proposed for stationary applications. So hydrogen storage capacity based on the alloy was referred to one weight percentage. That means 10 grams of hydrogen per kg of alloy. So mass of the metal hydride filled in the reactor is 30 kg. Operating conditions from 40 degrees Celsius to 140 degrees Celsius. So pressure development up to 200 bar. So from the hydrogen, impure hydrogen, initially will be sent to the metal hydride, where the purification will be carried out. Then the purified form of hydrogen will be sent to 3 different metal hydride reactors in individual or single stage reactor, which develops the pressure from roughly 20 bar or 30 bar to more than 200 bar, and the temperature range of 40 degrees Celsius to 140 degrees Celsius. The high pressure hydrogen will be stored for required application. So this is for stationary application. The heat transfer fluid circulation was designed to 20 to 30 liters, and the heat energy carried by each reactor is 145 kilowatt. So this is one of the layout proposed for one of the projects. Similarly, automotive application, the same approach. Instead of 3 individual reactors, 3 stage reactors are connected to increase the pressure. The same operating temperature and other conditions remain same, but to increase the pressure for transportation application, if we increase the pressure, what happens? Definitely the amount of hydrogen stored inside the container will be increased. So for that purpose, the pressure up to 700 bar was preferred by integrating three different reactors, which is the three-stage hydrogen compression. So this is another application for refrigeration. So for refrigeration and heat pump applications, initially hydrogen is filled assumed in the reactor A. So when you supply the heat, hydrogen transfer will take place from reactor A to B, and hydrogen will be absorbed. So this process is carried out at a high pressure. Once hydrogen is completely absorbed by reactor B, then you supply the heat, that is heat transfer fluid from high pressure or high temperature to medium temperature, similarly medium temperature to low temperature. So this setup from high pressure to low pressure, similarly low temperature will attain. Once it attained, you release the hydrogen from reactor B. During that time, when the hydrogen is released, already this reactor is at low temperature, probably atmospheric temperature 20 degree or even 25 degrees Celsius. The moment when hydrogen dissolves, immediately this reactor goes to less than 0 degrees Celsius. That low temperature can be carried by the heat transfer fluid. So keep on circulating the heat transfer fluid over that time, we can able to achieve space cooling applications or refrigeration applications. Here, the main advantage is there is no moving parts like a piston cylinder arrangement, and also safest method of hydrogen exchange between the reactors. So this concept is analyzed by numerical approach and observed that different type of alloys, how we can able to select by plotting the want of plot, that is the characterization study. From the characterization study, one can able to choose the alloy from the reactor A and the reactor B to achieve the operating pressure and temperature. So what are the assumptions that are required for constructing the heat pump refrigeration? Basically selection of the alloy. So we have conducted some numerical analysis. What is the time duration for taking the entire cycle, right from the first off cycle carried at high pressure, then sensibly cooling it, then hydrogen dissolve at low pressure region, and sensible. So complete cycle, how much time it takes for achieving the temperature of less than atmospheric pressure. So this analysis help us to construct the experimental site. So roughly around 1470 seconds if the entire reactor is submerged into the water, and the other approach, if the water is circulated in the reactor, maybe large capacity of reactor, heat transfer fluid is circulated over the what is that reactor, it takes around 1700 seconds. So like that, a different combination of alloys were chosen and the operating temperatures. From these, what is the performance of the refrigeration was calculated. From this, probably the zirconium based alloy is giving high coefficient of performance, and at the same time specific cooling power, that means how much wattage of cooling is done for the total mass of the alloy used. So at the same time, we have to see the specific cooling power. Though COP is high, specific cooling power is relatively low, but in such a case, the other combination of alloy is giving. So we have to choose, depends on the cost factor and depends on the cooling effect. We have to choose which alloy pair is suitable for our requirement. Similarly, whatever the temperature we want, maybe still lower than atmospheric minus, we can go for double stage or different combinations of metal hydrides. We can go for constructing the heat pump or refrigeration. So this is the hydrogen compression approach. For hydrogen compression, as I said, increasing the temperature from atmospheric temperature. See here one of the test condition we carried out, 25 degrees Celsius at atmospheric pressure. As per the available temperature, if you increase it to 60 degrees Celsius, delivery pressure will be 92 bar. From atmospheric pressure to delivery pressure 92 bar. If you increase the temperature accordingly, the delivery pressure is increasing. See 510 bar at a temperature of 120 degrees Celsius if we choose titanium based alloy. So this calculation help us to design the reactor and also fabricate for the compression experiment. So you can see here depends on the alloy characterization. Maybe here we are getting high pressure ratio, probably 24.2. But if you increase the temperature, the transfer of hydrogen will decrease. Quantity of hydrogen transfer is decreased. So that leads to less capacity of hydrogen only will be compressed. Whereas this one, you can see here 6.5 pressure ratio, moderate hydrogen transfer. Here, still low pressure. So preferably this second one will be good for hydrogen compression over the significant quantity of hydrogen. So the idea how the compression is carried out maybe for a single stage to two stage. So first absorption will be carried out, close all the valves, compress it by supplying the heat transfer fluid. Then from first stage to second stage, still the pressure will be increased. You can see here like that. If we go for two stage and three stage multi-stage compression, we can able to achieve the required pressure. On board applications, this is another case study that we have carried out for stationary application and mobile applications. So based on this analysis, why we are focusing for hydrogen, maybe faster recharging, long range, the filling will be helpful for traveling the vehicle, lightweight, and even for cold countries, even sub-zero temperature less than the 0 degrees Celsius also, this hydrogen based vehicle will start and zero emission. So once you compress the hydrogen, the complete setup has to be kept inside the vehicle. So higher the pressure, which shows higher the quantity of hydrogen filled in the reactor. So there are different type of hydrogen storage tanks named type 1 up to of 200 megapascal that hydrogen will means the vessel will withstand. The fabrication of the alloy is steel, only pure steel. Indirectly the weight of the vessel will be increased. Type 2 cylinder 250 megapascal and some reinforced materials with all stainless steel is used. Type 3, type 4, type 5 like that. Different categories of storage vessels are used. Directly the pressure will be increased. So we have conducted some numerical analysis. After compressing the hydrogen, that will be stored into a separate way, a separate container. So that separate container we have focused on for type 4 cylinder. Using ANSYS workbench, we have done a mathematical modeling to see the hydrogen storage at the elevated pressure of 700 bar at a different mass flow rate. You can see here how much time has taken and what is the rise in temperature inside the vessel. Say for example 0.01 kg per second. The rise in temperature with respect to time is almost 250 seconds from atmospheric temperature to 370 degrees Celsius. So this temperature rise indirectly reduces the efficiency of the filled container. So the allowed temperature is 360 degrees, 360 Kelvin. If it goes beyond that, the material will lose its inherent characteristics. So the rate of hydrogen filling is very crucial in the type 3 or type 4 cylinder. So we have done at a different configurations the inlet position at a different mass flow rates. From our analysis, the 0.02 kg per second flow rate at the inlet of around 257.5 mm from the one end. This gives the best filling option or filling rate. Others are giving them temperature variation, and also the rate of filling is very fast or late. So this is the another study. From that, depends on the mass flow rate, what is the rise in temperature in the storage vessel, and also change in pressure. So from this, as I said, 0.02 kg per second reaches almost 5 minutes to 7 minutes of filling at a pressure of 70 megapascal. Though the temperature is increasing, gradually the temperature leads to decrease here. So the allowable limit is, as I said, 360. So mass flow rate of 0.02 kg per second is less than the ultimate value of the preferred temperature. So renewable energy, if you see, almost various approaches the Indian government is focusing in order to meet out the demand and also to save the environment. See, there are various approaches. Alternate fuels such as hydrogen, biofuel, or synthetic fuels are focused. Then green initiatives like utilization of hydrogen gases that leads to substitution of fossil fuel systems, and green initiatives for power generation, direct power generation. Then stand alone without integrating with the grid, stand alone systems are giving the preference, and also subsidies to reduce the cost effective energy for cooking, lighting, and various approaches. And various other schemes like megawatt scale grid interactive renewable electricity is also Indian government is focusing to the substitution of fossil fuel based electrical generation. And these are all the various schemes are announced by the Indian government. Say for example, solar mission, national solar mission, PM Suryagar. So in all of the houses, we can keep the solar PV to produce the electrical energy for their required need. In this, National Green Hydrogen Mission is one of the goal where this hydrogen, wherever is possible, the Indian government is giving the subsidy and also encouraging a small community to the large capacity of the city. How effectively this hydrogen can be implemented. They are giving various projects and various schemes to meet out the demand and to save the environment. So based on that National Hydrogen Mission, recently Cochin Shipyard, they developed a purely hydrogen based fuel cell power a ship which is of around 50 kilowatt electricity is produced, and the ship will run around 8 hours continuously. So in this ship, they installed capacity of hydrogen is around 40 kg. So you can imagine that this 40 kg of hydrogen filling in the ferry for a maximum duration of 8 hours running. So what approach they may be followed? So at present they are using the compressed method of hydrogen storage. So maybe the solid state storage is still under research due to the low capacity of hydrogen storage. So in future, maybe one can able to adapt with metal hydride to fill the hydrogen of 40 kg. One can save the electrical energy which was used. And this is another Indian government initiative, that is hydrogen powered train, which is fully fabricated, constructed by our within India, Integral Coach Factory, Chennai. They successfully conducted the test in the July last year, 2025. So this train was fabricated or constructed for traveling of around 89 kilometer, and they tested in Jind, Sonipet, in Haryana, the Northern Railway Division. So here the maximum capacity of around 2,600 passengers can travel. 8 to 10 coaches are there. Total hydrogen storage capacity used for running this vehicle is 3,000 kg of hydrogen, where 2,320 kg low pressure hydrogen and 680 kg of high pressure hydrogen. So basically, at the high pressure hydrogen, we need more energy to compress the hydrogen. So this may be utilized in the beginning. Once the hydrogen level is decreased, they can go for 680 kg of this high pressure hydrogen vessel. Basically, this is a kind of a buffer. So here, each storage vessel of around 220 carriers are there for storing the hydrogen for around 2,600, storage capacity of 4,000 kgs of hydrogen. 430 kgs of hydrogen. So these are the government initiatives for public transports. Maybe in future, the main challenge is to overcome the storage for onboard application rather than a compressed method of hydrogen storage. One can target for metal hydrides in the upcoming years. So overall, if you see, metal hydride offers a high storage density, of course, and effectively one can able to store more amount of hydrogen, provided research on the metal hydride alloys need more time, and also this is one of the safest method application suitable for diverse applications in any sectors, right from the transportation to energy, and hope in future this technology can be implemented for various applications. Thank you. So these are the references. Kumar sir. Sir Muthukumar sir. If you have any queries, just I have given you an overview of complete the future perspective, how the metal hydride can be implemented in various applications. If you have any queries, please. If you don't have any queries, please. Muthukumar sir. Meeting going into.
Meeting with this.
Sir? One second, sir.
Yes, sir. Sir, any queries? Any suggestions?
Sir?
No, sir. Please, sir.
Sir, I don't think any questions are there. There are some presentations. People are telling that your presentation is good, sir.
Thank you, sir.
Usually some questions will be posted. Because of your clarity, I think there is no questions in this session. Sir, may I ask one question, sir?
Yes, sir. Yes, sir.
Yes, sir. Like, if students want to do any kind of small projects related to hydrogen energy in the capacity of UG, most of us are dating students in the undergraduate level. So, in
Okay.
what small project they can take.
Yes, sir. Yes, sir. Of course, sir. So basically, numerical studies, there are a lot of scopes are there. Provided here, we developed a small demonstration of sievert apparatus where we can analyze the characterization of metal hydride for different alloys, and also planning to develop a compression approach for a single stage and a two stage. So I have shown one of the reactor where 0.5 kg of hydrogen can be stored. So with that setup, we are planning to go for the hydrogen compression of around 50 bar.
Okay, sir. So, what setup will be required at engineering college like us? We don't have any basic setup.
So probably for fabricating this setup, it takes nearly 15 lakhs, sir. So major components are the vacuum pump, where we need to achieve 10 power minus 3 millibar to 4 millibar. Then reactor, the reactor itself we fabricated as per our design of, as I said, 0.5 kg in order to circulate the heat transfer fluid at the outer circumference. and inside metal hydride will be filled. So this fabrication of reactor itself takes 1.75 lakhs. So like that, the important equipments, if we plan, around 15 lakhs it came, sir. Thermostatic bath, then some of the measuring devices like thermocouple, pressure transducer.
Okay, sir. So any questions from the audience? May I direct your email ID, sir? Like, do you want to
Sure, sure.
contact
So
me?
basically, this is under still research,
Oh,
and metal hydride concept is not commercially implemented because of low capacity of hydrogen operating on the metal. But if you talk about the government, policies around the percentage pages of hydrogen, they are operating for ships and the trains. So to meet that much capacity of hydrogen, we need a long way to travel in the research side for storing the hydrogen.
sure, sir. Sure, sir. You clarified regarding this concept of hydrogen production to storage, even to the supply chain. So if in future any students have any kind of research related queries, I will direct you directly to you, sir. One of my
Sure, sir.
UG student is currently in your under your guidance, Mr. Ranjit. Likewise, I want to send a FOCA student so that this kind of hydrogen green energy will be coming up in the community as a new
Sure.
trend. Sure, sir. I will do my level best to help you in this space. Sir.
Definitely, sir. Definitely.
Thank you.
I can do that.
Thank you very much, sir. It was a nice.
Numerical. Basically, I was a numerical person. Even during my PhD also, I developed my own code for the compression and heat pump applications. Because of recently we received this DST funded project, we fabricated that setup.
Okay, sir. Okay, sir. Anything is possible, sir. We have to do some kind of base.
Sure, sure.
Thank you very much, sir. Let us wind up the
Thank you.
session. Thank you, sir. Audience, they're leaving today. Tomorrow we'll be joining at 10 a.m. We'll say goodbye to our beautiful professor here. Thank you, sir.
Thank you, sir. Thank you everyone.
Sir, the session has ended, sir. Today we are winding up. Any questions you may ask to Satish, sir? Muthukumar here, sir.
you.